This is the second section in methods in differential equations, and here we're going to be looking at second order homogeneous differential equations. So the first thing, second order, what does that mean? Well, first order was dy dx. Second order means that it contains something like this in there. Okay, so you could think of it as at some point it's been differentiated twice to get to this stage. So I suppose to go back, you almost need to think, right, you need to integrate twice to go back. Okay, homogeneous, well, that word in mathematics just means the same degree, which normally means the same power, and differential equations, well, we know about. Yeah, so second order homogeneous differential equation, and actually in this particular case the homogeneous means equal to 0 will look like this. So it will be a second derivative with some sort of coefficient of a there, then another coefficient in front of what the first derivative is, plus another coefficient in front of y equals 0. So this is what a second order homogeneous differential equation looks like. So we need to go about solving this. So the first thing we're going to do, we're going to gather these coefficients here, a, b and c, and we're going to form something called the auxiliary equation, and the auxiliary equation looks like this. So it'll be am squared plus bm plus c equals 0. So this is called the auxiliary equation. So we just get those coefficients a, b and c, and we use it to form a quadratic, basically, like this. Now we'll call the roots of this auxiliary equation alpha and beta, and depending on the discriminant of this auxiliary equation will tell us how we use alpha and beta in finding the solution to this. So there are 3 different cases or values for the discriminant. So it could be that the discriminant b squared is greater than 4ac. Now if that's the case, I'm going to write down in each case down here what our general solution will be. So we found our auxiliary equation, we've worked out the discriminant, we found the roots. Then if b squared is greater than 4ac, then the general solution of our second order homogeneous differential equation will be y equals a, and this is an arbitrary constant, e to the power alpha x plus b e to the power beta x. Okay, and in all of these cases that I'm doing, a and b are going to be arbitrary constants. Now the reason why I've got 2 constants, if you think about it, if you've differentiated something twice, if you're going to integrate back, when you integrate this once you get a constant, then when you integrate it again you get another constant. So let's just put down here where a and b are arbitrary constants. So this will be the general solution. Finding the values of a and b would give us the particular solution. Right, if b squared now is equal to 4ac, then our general solution is going to be y equal to, and this can be factorised to a plus bx, So again, a and b are arbitrary constants times by e to the power of alpha x. So I'll just underline where our roots are, alpha, beta there. Only one root here, alpha, because this tells us there's only one root to the quadratic. Then the last type is going to be when b squared is less than 4ac. Now you know from core 1 that means that you have complex roots, and I'll write down what the general solution is and then a little note about alpha and beta being complex roots. So the general solution will be y equals e to the px, and then this can be factorized, so a cos qx plus b sine qx. Okay, now this is where p and q are the complex conjugate roots alpha and beta. Okay, so where p and q are the complex conjugate roots alpha and beta. Yeah, so p and q just denoting the fact that they're part of the complex roots. So basically it's going to be like p plus qi or p minus qi. So really I suppose should have said that p and q are the real and imaginary parts. So let's correct that. They're not the are the. Let's correct that. Where p and q are the real and imaginary parts of the complex conjugate roots of alpha and beta. That's more like it. Okay, so we want to find a general solution to this equation here. Now we don't need to form the auxiliary equation for this. It's quite straightforward. We're going to integrate it twice to work out what the solution is. This is just to show you that we end up with two arbitrary constants. So let's integrate it. First of all, like this. So integrating it once then will leave me with dy dx, and that will give me 6x squared plus, and I'm going to call this arbitrary constant a. Then I want to integrate that to find out what the constant is, what I get the second time. I should really be writing dx after these when I integrate. Anyway, so I will then get y equals, this will be x2x cubed plus, now the a becomes ax, and then another constant b. Okay, so we just solve this by integrating twice. Right, so in part A we need to find a general solution to this equation. So first of all, we want to find out what form the solutions are going to take, and whether we're going to have two real solutions, one real solution, or imaginary solutions. So I want to work out b squared minus 4ac. So a is 2, so that's this value here, there's b, there's c, so they're the values I want. A is 2, oops, b is 5, c is 3, So if I work out b squared, let's do b squared minus 4ac. Minus 4ac, that's going to be 25 minus 24, which is 1, which is greater than 0. So I know my solution will be of this form: y equals a e to the alpha x plus b e to the beta x. Now this result and the others are not in the formula book, so you do need to remember what they are. Okay, I've put them here in the questions, but in the exam you will need to remember that for each case what the results are. So I'll just put here what I actually did. So that's the same thing, isn't it? B squared minus 4ac is greater than 0. So now we form the auxiliary equation, which is going to be 2m squared plus 5m plus 3 equals 0. I want to solve that auxiliary equation, so we know it's going to have 2 real roots. So I've got plus 3 and plus 5. So this needs to be 3 and that needs to be 1. I could use the quadratic equation if I wanted to solve it. So then I'll get my two values of m. So I'm going to have 2m plus 3 equals 0, which will give me 2m equals minus 3, which gives me m equals minus 3 over 2, and then I will have m plus 1 equals 0, which gives me the other solution, m equals negative 1. So I'll just highlight those. These are my values of alpha and beta, and it doesn't matter which way around. So let's call that one alpha, let's call that beta, or you could have done it the other way around. So now we can write our solution as the general solution: y equals a e to the alpha x, so my alpha was negative 3 over 2, x plus beta e, b e to the negative x. So here's my general solution. Right, now part B, we need to show that that general solution satisfies the equation. So in other words, if I do 3 lots of this plus 5 lots of this differentiated plus 2 lots of this differentiated twice, I should get 0. So let's try that. So let's work out what dy dx is. So that will be minus 3 over 2 a e to the minus 3 over 2 x minus b e to the minus x. So that's what we get when we differentiate once. When we differentiate twice, we'll get 9 over 4 a e to the minus 3 over 2 x plus b e to the minus x. Right, so let's see what happens when I do 2 lots of what I get when I differentiate twice, plus 5 lots of what I get when I differentiate once, plus 3 lots of y. So that will be 3 lots of 9 over 4 a e to the minus 3 over 2 x plus b e to the minus x plus 5 lots of this. Got to be careful with the minuses, I don't miss them out. Plus 3 lots of, let me correct this, 3 should be a 2, sorry about that. Plus 3 lots of y, so 3 lots of this. Right, let's see what we get. with that. Right, so expanding the brackets. From the first bracket, these two, so that will give me 18 over 4, which will be 9 over 2. So 9 over 2 a e to the minus 3 over 2x. Let's do all the a terms. Minus 15 over 2 a e to the minus 3 over 2x. So that's from multiplying that out. Then the last one will be plus 3 a, not the last one, but of the a terms will be that. And then from the b terms, multiplying all the b terms by 2, so I'll have plus 2b e to the minus x minus 5b e to the minus x plus 3b e to the minus x. Now all of that cancels out, giving 0. If you add these together, 9 over 2 minus 15 over 2 gives you negative 6 over 2, which is negative 3 plus 3 is 0. 2 minus 5 is negative 3 plus 3 is 0. So we get 0, so hence y equals a e to the minus 3 over 2x plus b e to the minus x is a general solution to the second order differential equation. So this example is different. We don't actually need to solve this equation. This is the solution. We want to show that this is a solution. So it means differentiating it twice. When we differentiate it once, we'll put it here. We'll take away 6 lots of this differentiated. We'll add 9 lots of this, and we should get 0. Now let's write down what y equals here, and I'll probably start by expanding the brackets. It'll make it easier to differentiate. Now this is not part of the question, but if you look at this and look at what it's the solution of, it's the solution when b squared equals 4ac, or when b squared minus 4ac is 0. Okay, now what does that mean? That means our auxiliary equation gave us one repeated root. And we should be able to get that root. The root is here, 3. So even though we're not asked for it, you can see, right, the auxiliary equation would have had a root of 3, like this. That's a root of 3. If we expand that, we'll have m squared minus 6m plus 9 equals 0. Now remember these numbers, a, b and c, so not really there. Let's put one at the front there. So these values of a, b and c, where did they come from? Well, they came from here. Yeah, so it all fits, it all goes together. Anyway, back to the question. Let's work out dy dx. So the first term will become 3a e to the 3x. Then for this we need to use the product rule. This will be u, this will be v. Remember the product rule is uv dash plus u dash v, or vu dash. So u times by v dash plus u dash times by v. I'll tidy that up, and that will give me this. Right, we'll now differentiate it a second time. So we'll have 9a e to the 3x. Now, just like before, we're going to use the product rule on this. So we'll have u, which is 3bx, times by v dash, which is going to be 3e 3x, plus u dash, which is just going to be 3b, times by v, which is e to the 3x, and then plus the 3b to the e to the 3x. We'll simplify that. So that in the bit in the middle becomes 9bx e to the 3x, and then the 2 at the end go together, 6b e to the 3x. So to show that this is a solution, we're now going to do one of these here, plus, or take away 6 of these, add 9 of these, and it should make 0. Okay, so let's write these down. So d squared y dx squared minus 6 dy dx plus 9y equals, right, so I think what I'll do is I will just write one underneath the other, so I can easily add and subtract. So this will be my d squared y over dx squared, like this. Then I'm going to take away 6 lots of this, so I'm going to write them times by 6. So I'll have negative 18 minus 6, so negative 18 negative 18 and negative 6. Not sure what's happened to that b. And then underneath I'm going to have 9 lots of this. So I'm going to plus 9a e to the 3x's, and then take away, add 9b x to the 3x's. Now if I add all of those together, I get 0. Okay, so that shows that this does satisfy this differential equation. Right, here we want to find a general solution to this differential equation. So first of all, we'll write down our values of a, b and c. So a equals 1, b equals 8, c equals 16. We'll form our auxiliary equation, which is going to be m squared plus 8m plus 16 equals 0. At the same time, we'll work out what b squared minus 4ac is, and that will be 64 minus 4 times 1 times 16, which means it equals 0. In other words, b squared equals 4ac, which means that the general solution is going to be of this form: y equals a plus bx, just like the last example was a general solution, e to the alpha x, and the e will be, this will be whatever that root is, which we're going to find over here. So yeah, let's factorize this. There should only be a single root, So I'm going to have m minus 4 all squared. So yeah, the single repeated root is 4. Okay, so that's my value of alpha. So all I need to do is just plug that in. So general solution is y equals a plus bx and then e to the 4x. Now can you see how easy that was? So even though it's a second order differential equation, actually solving it wasn't really that difficult once you've got that auxiliary equation, especially if it's just got one real root. It's very easy. Okay, here we want to find the general solution to this differential equation. So I'm going to have a equals 1, b equals -6, c equals 34. So it might be worth working out what b squared minus 4ac is, so I know the type of solution, even though it's already in the box there. So -6 squared minus 4 times a times 34. So that's going to be 36 minus, I think that's 144, 36 times by 4. Sorry, 34 times by 4. No, not 144. 136. Okay, so that's going to be -100. So b squared is less than 4ac. So that means I'm going to have these complex roots. So I'll still form the auxiliary equation. So m squared minus 6m plus 34 equals 0. Now this one I know isn't going to factorise because I'm going to get complex roots, so it's probably easier to use the quadratic equation. So minus b plus or minus the square root of b squared minus 4ac. Now I could have just written down -100 because I already worked that bit out, all over 2a. So from this I will get 6 plus the square root of -100 over 2, and here I'll get 6 minus the square root of -100 over 2. So I can see that square root of -100, that's going to be 10i. So that'll be 6 plus 10i over 2, which is 3 plus 5i. So the other one's going to be the conjugate, so I know that's going to be 3 minus 5i. So that'll be 6 minus 10i over 2. So in the general solution, p will be 3 and q will be 5. So we can now write down the general solution as y equals, just going straight into this. Now again, you need to memorize this, it's not in the formula book, equals e to the px, that's from 3x, and then a cos, so q is 5, and then b sine 5x. So there's our general solution. Okay, last one here, find the general solution to this differential equation. So a is 1, b is 0 this time, and c is 16. So we're still going to follow this out the same way. So let's work out what b squared minus 4ac is. So that will be 0 squared minus 4 times a times c. So that gives us negative 64. So b squared is less than 4ac, which means the general solution is of this form. Now, I would get used to, when you're doing these questions, I'd get used to actually writing out, once you've worked out b squared minus 4ac, writing out what the general form of the solution is, so it just gets into your head, so you're not referring back to the book every time, because they do need to be memorized. Right, let's form our auxiliary equation, which is going to be m squared minus 16 equals, plus 16 is 0, which means that m squared is negative 16, and if we square root both sides, m is going to be equal to plus or minus 4i, yeah, because you know you're going to have m is equal to plus or minus the square root of negative 16. So that's where we get the 4i from. So looking at the values of p and q that go in the general solution, b is going to be 0 this time, and q is going to be 4. So our final answer is going to be y equals 2. Now, since p is 0, this just becomes 1, so we don't need that anymore. We can just write down a cos 4x plus b sine 4x. Right, you should now be able to do exercise 7b on pages 156 to 157. So I've summarised, or you've got a summary here of the different cases and the different types of general solutions. So we look for our values a, b and c here. They form the auxiliary equation which we solve, depending on the types of roots of our auxiliary equation. So when b squared is less than 4c, this is when we get 2 real roots, and if there are 2 real roots, and those 2 real roots will be alpha and beta, then they go into the general solution, which is going to be look like this. When we have b squared minus 4ac equals 0, or b squared equals 4ac, in this case we'll just have one real root, or one repeated root, which we'll call alpha, and if that one root is alpha, then the general solution is going to look like this. And the third case is where we have b squared minus 4ac is equal to 0, or 4ac is less than 4ac. Did I say b squared is less than 4ac? Not sure, doesn't matter. Here we have 2 complex conjugate roots, yeah, and they're conjugates of each other, and those conjugate roots are going to be in the form p plus or minus qi. So it's these values of p and q that go into our general solution, which will be in this form. Yeah, and if our auxiliary equation just has roots which have no imaginary part. So if the roots, sorry, not an imaginary part, no real part. So if the roots have no real part, so e.g. they're of the form just plus or minus qi, then the general solution just becomes y equals a cos q plus b sine q x and x.